Okay, so let's go through these in order. And the first was that we have this problem of the one that we discussed in the last class, right? This is the first problem, is that correct? Where there's a mass hanging on a pulley like this. Is that right?
Yeah.
And I went over that problem from the perspective of...
Out of order, so
that's okay. I'm catching on. Okay. Then there's a moment of inertia associated with the pulley. And the pulley also has a radius r. And the first thing, the way I worked it out in class last time was to look at all the forces and look at the equations of motion for the individual bodies, 3 bodies involved. The linear accelerations of the 2 blocks and the angular acceleration of the pulley. Okay, so, and I didn't get to email these podium notes out because apparently the server was down. So I'm going to also get that to you this afternoon as the podium notes from last time. Okay, but this, for today's homework, you're to approach it from the perspective of the work energy theorem. So just like we did maybe this problem before where we neglected the moment of inertia of the pulley, we had the kinetic energy of the 2 masses moving together and the potential energy of gravity, so that the work done by gravity showed up as kinetic energy of the translational kinetic energy of the 2 masses. Now it's very much the same, except we add in the rotational kinetic energy of the pulley, which is going to be related in a very simple way to the velocities of the masses. So the no-slip condition gives us that the let me say that the rotational velocity, the angular velocity of the pulley, is related to the translational velocity of the masses. Both of the masses travel at the same velocity. And the pulley is turning without slipping. That is, the rope over the pulley turns the pulley without slip. So this is the no-slip condition for the rope on the pulley. Okay, so now we apply the work energy theorem. We don't even really have to go into very much detail here. We only need to examine the work done on the system. The initial kinetic energy is 0 because it begins from rest. So we can compute the kinetic energy of the system after the mass has dropped. M2 has dropped some distance d. Okay, so if this pulley, if this mass drops a distance d, then the work by gravity will be simply m2 gd. Right? Now there are lots of other forces in the system, but none of them do work, except gravity. Gravity is the only one that does net work on the system. So the net work by all the different forces on this system ends up being the only one that ends up in net having anything is the work done by gravity. What about the ropes? Why don't the ropes do work? Right, there's tension here, and tension here, and there's even tension here that's going to do work. All of those are spinning things, moving things, but they don't end up in the net work. Why is that? Because they're moving. One is there's a positive contribution in one place and a negative canceling contribution in another place. We encountered this before when we had with the system where we neglected the moment of inertia of the pulley before. In that case, the tension was the same all along the rope. Remember, we had that same tension on both ends, and we had M1 and M2. And then the amount of work done pulling the mass on the table a distance d would have been Td, but then this mass moves the same distance down, and the amount of work there is minus Td, so the net work done by the rope is 0. So there's really only the work of gravity in this problem that that comes in. So all we have to do is account for the work done by gravity. Another way of thinking it is to look at the potential energy. There's no friction. I should say there's no kinetic friction. There is static friction, but static friction does no work. Why does static friction do no work? Yeah, there's nothing moving. It's static. There's no distance over which it's displaced. So if you look at the potential energy of the system, then there's only gravity that only the position of the block is changing. So the only change in potential energy is because the block that's hanging has dropped the distance d. The block sliding across the table, well, there's no change in potential energy associated with horizontal motion due to gravity, and there's no kinetic friction. Okay, so therefore, all we have to do now is account for the kinetic friction, the kinetic energy, the final kinetic energy. If both masses are moving at the same speed, then they each contribute an amount that's proportional to their masses and the square of the velocity. And now we have to take into account the rotational kinetic energy of the pulley. And we said that because of the no-slip condition, that angular velocity is related in a simple way to the velocity of the blocks. And so we can write it m1 plus m2 plus I over r squared. V squared. You could write it like that. Which then makes it easy to solve for the velocity of the blocks at the end. So that would give you then the velocity is going to be 2m2gd divided by m1 plus m2 plus the moment of inertia over r squared, square root of the whole thing. And I think we had this problem neglecting the moment of inertia of the pulley previously, and so you could go back to check that one, to check with previous work, set I to 0, and that should correspond to the problem that we did before, where we did the problem using work energy theorem for exactly this system, but neglecting the rotational kinetic energy of the pulley. Okay, so let's see now. If we add the massive pulley in there, that it has a big moment of inertia, then the velocity for the same drop, is that going to be greater or less than the problem where the pulley is massless and has negligible moment of inertia? So let me ask that question again. We have two different problems. One here is where we neglected the moment of inertia of the pulley, and the other is where we have the moment of inertia of the pulley. Let's suppose we have these two systems and we let them both drop at the same distance, d. Which one is going to be traveling faster?
The one without moment of inertia.
Right. And why is that? Do you have an explanation? I mean, it's certainly true, and that you can get from this relationship here. If you set I to 0, you get a bigger velocity, right? So, Mr. Flanagan, do you have any other explanation other than the formula gives it? Why should the one with a very massless pulley end up with a higher velocity?
Because it takes force to turn the pulley.
Okay.
And it's got mass.
Does that directly get you to the fact that its velocity would be lower?
Some of the force is put into having angular velocity instead of all of it just being on the block.
Yes, you have to accelerate, create an angular acceleration of the pulley. In the case where you have a massive pulley with moment of inertia. Another way of thinking about it is in terms of the energy. The potential energy goes into kinetic energy, and when you have the pulley spinning, you also have the kinetic energy of the pulley. And so that means there's going to be less energy left for translational motion of the blocks. So that's another way of same thing. You can either do it by force or by work, by energy. Okay. Any questions about that? What do you think of this? Did it puzzle you? Did it make sense? Okay, you should be able to work this problem. This is got some parts to it, but you should be able to work this problem both in terms of force and in terms of energy. And just like what we discovered before, the energy question, the energy method, is a quick way of, for example, finding the speed after it goes a distance d. but you can't find very easily. I mean, you can find it, but it's a little bit harder to find how long does it take to get to that distance. You know, the time it takes to travel that distance or other things. It's a little easier to do that with forces. But you should be able to do this problem both ways. Find the velocity at the end both ways. Oh, let me ask one more question before Mr. Disharoon. What kind of motion is this? Obviously, there's two kinds. There's rotation and translation. So let's consider the translation. What kind of translational motion is it? Say it again.
It should be uniform acceleration.
Uniform acceleration, right. The forces are constant. They're not changing. And the mass is not changing. Therefore, we get uniform linear acceleration of the masses. And how about the pulley?
Uniform rotational acceleration.
Yeah, uniform rotational acceleration, uniform angular acceleration. So the angular velocity is increasing linearly with time, just like the translational velocity of the blocks is increasing linearly in time. Mr. Disharoon.
I saw like on 24 when we were looking back at it, we subtracted the force of kinetic friction from the first mass. So we said we had the work done by the mass 2 with gravity, but then we subtracted the kinetic friction.
Okay, so we could add, I think, in other words, there's kinetic friction here, right? So we could add that into this problem. Which would be, maybe we didn't do this problem without kinetic friction, so that's another component of this.
Oh, okay, so we didn't use friction at all?
Well, I'm not sure exactly what, but in this case there wasn't any friction stated in this problem, right? Is that right?
It would have made my life so much easier if I would read the whole question.
Okay. Okay, so in this problem, the way it was stated, I didn't intend for you. In fact, it says there is no friction between the masses and the surface.
I got it.
It says that right there. Okay. Now you could add it in.
I did too.
Ah, all right. Well, how would that change this? Then the work done, you have to subtract out the work done by kinetic friction, and that will slow the mass down. And at the end, it's got less velocity. So you would, if you were going to do that, it would be mu k times n, which is m1g times the distance. Okay. So where there's an m2 here, we would replace that by m2 minus mu k m1.
What about friction
And
on the pulley as well?
What's that?
The friction on the pulley?
I said there was.
Yeah,
Yeah, you're going to put friction on the pulley too. Okay.
Do that too?
So we don't.
Look how big the answer is.
You like making it complicated, don't you? There could be. We haven't really considered friction associated with rotation, a kind of kinetic friction associated with rotation, which might be the friction of the pulley on the axle. You could put that in, but the principles remain the same, right? You can use the work energy theorem as long as you can account for the work done by conservative and non-conservative forces. They're all coming into the work. So the principle remains the same. It's just it becomes increasingly, more complicated, more steps. Okay. So next problem then is the one where the ball is rolling without slipping down a distance d down the inclined plane. So down a distance d down the inclined plane, it rolls like that, and without slipping, it says, and we're given I'm going to change the name of the angle to alpha because one might be inclined to use theta for the rotational motion of the ball. I don't care. Okay, so diagram the forces acting on the ball. Note that friction must be present in order to make the ball roll without slipping. Why is that?
It needs to add friction to keep it from just
Moving across the surface.
Just
Like
slide
it-
down.
Get traction so it rolls.
Excellent, right. Traction is a good word. So suppose you had a block of ice, you had a cylinder or something on top, and then you inclined the block like this. The cylinder is just going to slide like that. There's nothing that causes torque on the cylinder. There's no friction present between the surface of the ice and the surface of the cylinder. So there has to be static friction present here. But it has to be friction present, and what kind is it? It's static friction, right? So it's going to be static friction. And why is it static friction? Because we're told that it rolls without slipping. Static friction is the kind that's appropriate where there's no slip between the surfaces. Okay, and then we have the normal force and we have gravity, and that's it. Those are the only forces present on this body. Okay. In spite of the presence of friction, the sum of kinetic and potential energies is conserved. Why is that? In other words, we only have to be concerned with the work due to the conservative force, which is gravity.
It's not using any of its energy to like cause heat on the ramp.
Right. It's not slipping, it's not sliding, there's no heat dissipated, so there isn't any work done by static friction. Static friction typically does no work. Okay. But we also don't know the magnitude of the static friction, right? We don't know its magnitude. We have to actually work out what the magnitude is from this. It has a maximum value, but in this case we actually have to work out what the magnitude of the static friction would have to be, which we could do here at the end if you're interested to see. But okay, so then the work is going to end up as increase in kinetic energy, and the kinetic energy starts off at 0 because it begins from rest. So, and it's very much like the problem that we just did. The work here is just going to be mg d sine alpha, where alpha is the angle of the ramp. Positive or negative? Positive because it's going in the direction, it's more or less in the direction of gravity, right? It's coming down some, depending on the incline. And then the kinetic energy, well, it's a combination of translational and rotational motion for that body. So it's both translational motion of the center of mass and then rotation about the center of mass. But we have also, given the condition that it rolls without slipping. This is the no slip condition. So therefore we can rewrite this in terms of the velocity alone and not just the angular velocity. The other way you could come up with this expression for the kinetic energy is to consider that at any given instant it's rotating around the point of contact, and then you could apply the parallel axis theorem. So in addition to the moment of inertia about the center of mass, there's the increase in the moment of inertia by the mass times the radius squared, which would get you the same result. See if you okay. Would you like me to demonstrate that? How it works both ways? Okay. So the other way to do it, other way. I want to find the moment of inertia about the edge, because it's instantaneously rotating around the point of contact. And the moment of inertia about the edge would be the moment of inertia about the center of mass, which is what I was calling I before, plus ml squared, where L is the distance between the parallel axes, and in that case it's the radius. And so the kinetic energy at the end is 1/2 I edge omega squared, which is 1/2 I center of mass plus mr squared, and omega squared is v squared over r squared, and that gives us the same result that we had before. So you could do it either way. You could say kinetic energy is a combination of translation of the center of mass and spinning around the center of mass. That's one way to account for it. God bless. The other way to account for it is to say instantaneously it's rotating around the point of contact, and then I can use the parallel axis theorem, and that accounts for all of the kinetic energy of motion, both the spinning, what we would call spinning, and translation if we look at it from the center of mass point of view. Okay, so and now you're to ask the question again. Really, it's the same question that I asked before. If the sphere, you have two spheres, same mass, same radius, but one of them is made of a dense material, and it's a hollow sphere. So all of the mass is concentrated on the outside of the sphere, on the shell. And you have another sphere which is made out of a less dense material, and it's solid. The two spheres have the same mass, same total mass, same radius. And how could you tell the difference between them? You just put them on the ramp and let them roll, and which one hits the bottom first?
The hollow one.
Does the hollow one hit the bottom first?
No.
The solid one hits the bottom first, right? It has the solid one has a lower moment of inertia. So in other words, another way of saying it is that they both are spinning at the same rate. One of them has more kinetic energy than the other one, right? Because the hollow one has more kinetic energy than the solid one. If they have the same total mass, right? You got to keep saying that caveat. They have the same total mass, it's just distributed differently. Okay, so there's more kinetic energy for the hollow one that's spinning at the same rate, because the mass has been distributed farther out from the axis of rotation. And so therefore the work done by gravity has to be distributed more into rotational kinetic energy than translational kinetic energy. So the one that reaches the bottom first is the solid one. Okay. In fact, we'll do that demonstration in class. I didn't have time to arrange that one today. Okay, any questions about that one? Okay, then we have the problem related to the number 4 and 5 in the book, which have to do with the pencil. And there's two situations here. The pencil is done in two cases, right? One of them is with friction, and the other is without friction. So you put the pencil on a table like this, and then let it fall. And the other one is to put it on ice. How will the two motions differ from each other? So we start them both off. Same pencil, same shape, same mass, same length, everything is the same. All we're changing is the surface of contact. In one case there's friction present, possibility of friction present, and the other one there isn't. How is that going to affect the way it falls?
The one without friction is the center of mass is going to fall straight down.
Good.
The pencil's going to,
yeah.
the bottom of the pencil's going to move.
Mr. Tremblay argues that the one on ice will fall in such a way that the center of mass goes straight down, so that when it lands, the center of mass will be right below where it was when it started, like that. Yeah. Why is that? It's good. I like it, but why? Can you explain why that would be?
The force of gravity that we've drawn before is always draw it as acting on the center of mass.
Right, that's the only force that's present. Well, there's two forces present. Right. I'm sorry. I spoke too quickly. What are the two forces present? There's gravity, which is straight down, and the normal force, which is straight up. So, considering the net force acting on the body, there's no horizontal force acting on the body, even if it tips, even if it's inclined. So let's incline it a little bit. If it were not perfectly straight, even if it weren't perfectly straight, there's gravity and the normal force. There's no horizontal component. So there's nothing to make the center of mass accelerate one direction or another. It has to fall straight down. Okay. Whereas when we have friction present, so we have, let's say, sandpaper here, when it starts to incline, in fact, there is a component of a force associated with friction, which let's suppose it's in that direction. Okay, now which way is it inclining? For the force of friction to be this way, which would it have to incline? What's that?
Towards the right.
Towards the right. So Mr. Covington wants to say that this body is going to be inclined to the right. Does that make sense? Is that going the right way?
Because the tip of the pencil is going to want to go to the left. Or
why?
No.
Ah,
No.
other way around.
Other way around.
Yeah, okay. Mr. Covington withdraws his nominee, and oh goodness, I have to take off every little dot here. Okay, so we're gonna incline it the other direction here. but I should do it in such a way as to make it have the point at the same place there, because it's going to keep the point. Remember, static friction works to oppose sliding of the point of contact. Okay, so the static friction is pushing it in that direction, right? To keep it from sliding to the right. It opposes the sliding to the right, so it's got to work to the left. And that means if I look at the net force acting on the pencil, it's to the left in the horizontal direction. So it's going to tip over to the left, end up falling over here. Okay, good. Okay, so then the rest of it is a consideration of the type of motion. In this case, in the second case, you could consider it to be rotation about the point of contact here. And so we need the moment of inertia about the end, about the tip. Yeah, I should say tip is better. Over here, what is the moment of inertia? It's the moment of inertia around the center of mass. But there's also, it's falling, but okay, but anyway, there's the two moments of inertia, and you need to be able to relate those two. So how can we relate those two? If I know the moment of inertia about the center of mass, I can find the moment of inertia about the tip. How do I do that?
It's shifted through the parallel axis theorem.
Right. So in one case, I have rotation. The one on the right, the ice, when it's sliding on the ice, it's rotating around the center of mass, and the axis of rotation is into the board. Well, coming out of the board. If I have use the right-hand rule, rotation is out of the board. And in the case on the right, it's rotating also by an axis that's parallel. And so I should be able to use the parallel axis theorem, where L is going to be the half length of this pencil here. It's the distance between the center of mass and the tip, whatever that is. Okay, so I can take those into account in this topic. Okay. Does anybody happen to have printed off the assignment for Monday? Anybody got that handy? Anybody worked ahead yet? I would like to preview, but I don't remember what we're doing. Has anybody got...
Yeah, I did it real quick.
Can you pull it up for me, please? Yeah, he's got his smartphones here. You have your laptop? Somebody? Yeah, I would be happy to have somebody. So we can... There may be problems from the book. I can't remember. It's the last assignment for Chapter 7.
Analyze the simple pulley illustrated and analyzed on page 182 to 184, except now assume that the pulley has mass and radius r and associated moment of inertia I. Find the acceleration of the masses and the tensions.
Ah, okay. So it's the Atwood machine. No, I got it. Thank you. Okay, so we're going to do the Atwood machine again. But this time we're going to do through forces, not through work energy theorem. We're going to do the whole problem in terms of all the forces. And we're going to say that the two masses are different, and the pulley has a moment of inertia, and a radius r. And the question is, what are the accelerations? And how about the tensions in the rope? What are the accelerations and tensions? So and in fact, you could ask, if you understand the tensions, you could ask that third question again, the one that we asked before. How much does this machine weigh? That is, what is the force exerted by the machine on the ceiling? Yeah. Remember, we did that before, neglecting the moment of inertia of the pulley. Now we can add that back in. Okay, so this is another one of these problems that this kind of repetition should be starting to sink in for you now when you're doing these things. What's the first step? Force diagram. How many bodies do we have? 3 bodies. So they're going to be all the forces on the 3 bodies. Okay, so obviously there's gravity acting on each of these masses. And there's tension, but the tension is not the same throughout the length of the rope. Now, one way to argue that, can somebody give me an argument or an understanding of why it is that the tension cannot be the same along the rope all the way along? There's a simple argument, physical argument, why the tension on this block is different than the tension on this block, on the rope at the attached to each block. So let's look at this one. So we have T1 here, T2 here, and then of course we have a T3, which would be the tension in the rope that's hanging down from the ceiling, and that would correspond to the weight of the assembly. Mr. Flanagan.
If the two tensions were the same, they would balance each other and nothing would move?
Yes, there would be no torque on the pulley. And so but it has a moment of inertia. If it has a moment of inertia but no torque, then it's not going to accelerate. So therefore, if you observe acceleration, and you do expect this to accelerate, therefore the only way around it is to say that those two tensions must be different. And you can think of it physically. The rope is trying to accomplish the connection between the masses, but it's also connected to the pulley. And so it's going to be trying to accelerate the pulley. And so therefore there is going to be a difference in the tension when it's going across the pulley, because it's got to accelerate the pulley. So it's pretty much the same argument. Okay, what's next? Coordinate system. Somebody like to choose a coordinate system? We could make all of them up. Mr. Trimley says up. So y1, y2, and we need another coordinate.
Clockwise.
Yeah, and Mr. Covington likes clockwise. Okay. That's fine. That's in this case, there's not a lot to argue for one way or another. You have to pay the penalty. The penalty you have to pay for any choice of coordinate system is you have to make sure that you get all of your signs correct in what's coming here. If you choose it one way, there's going to be some choice of the signs that connect all of these variables, right? So because the accelerations of the masses are not independent of each other, and neither is the angular acceleration of the pulley, they're all connected to each other by the rope. All right. So the next step, what's the next step? Say again? Well, we haven't written any equations. Yeah, the unknowns are going to be, you could probably figure out your unknowns here, which would be the accelerations and the tensions, right? So you could do it now if you like. Accelerations, the two accelerations, the two tensions. We got four unknowns at the beginning. Except that we know already, and the rate of, and the angular acceleration of the pulley, 5 unknowns. But you know already that you've got lots of relationships here. So let's write Newton's equations. So for each of the degree of freedom, there should be an equation for each degree of freedom. And we have 3 degrees of freedom, so we expect Newton's equation for each one. So how about the acceleration of the first mass? The mass times acceleration of the first mass is equal to?
Okay.
Yeah, but you're the one who chose it to go up, so remember it's going to be t minus m1g, right? You got to be careful there with the signs. You got to get your choice of coordinates is going to determine whether it's t minus m1g or m1g minus t. Okay, and the second one is going to be T1. There are 2 different tensions. T2 minus m2g. And then how about the pulley?
I alpha equals T2R minus T1.
Yes, okay. So let's write it down here. T2 minus T1, and let's figure out how he got that. So we're looking for an equation that looks like Newton's equation, but it's for rotation. The moment of inertia times the angular acceleration is equal to the net torque on the body. Notice that he's chosen theta to be increasing clockwise, so an increase, if this thing is going this way, accelerating this way, that's a positive acceleration according to theta. So we would like m2 to be greater than m1 would give us a positive acceleration in that direction. Okay. Now the torque acting on that body, there's three forces acting, four forces acting on that body. We didn't include an important force over here. Actually, it's not important for this problem, but it's present. So to be consistent, we should put it in. But it has no effect on the problem. Why does it have no effect? Yeah, we're looking at the rotation, and it doesn't produce a torque. So there's no torque produced. So let's look at each of these forces. I should, to be explicit here, let's go pull this figure down here and look at the torques produced by each one of these. So this is T1, T2, M, G, and T. Call it T total one, so let's call it total T. Okay, so we're talking about rotation about what point? What is the center of rotation of this thing? Yeah, the center. We're computing the rotation around the center. We've chosen the center to be actually the center of rotation here. So we need to calculate the torques. This thing has a radius r. So what is the torque produced by the weight? Remember, the torque is always r cross the force. And in this case, r is 0, right? The force is acting on the center of mass. So r is 0, so the torque produced by gravity here is 0. And the torque produced by the tension the torque produced by the rope that's holding the thing up by the axle, holding it up to the ceiling, that's also 0 because it acts on the center. So that's another one. They're both 0 because the radius is 0. It makes it easy. All right, is that clear why those produce no torque? If you take a wheel and hang it by its axle, it's not going to start accelerating because you're holding it up. Neither gravity nor the tension in the rope that you're hanging it from is going to cause it to accelerate. So then we need the torque due to the two tensions. Okay. Now in that case, r is in this direction. Here's the magnitude, and it has a vector in that direction. And r cross T2, are they perpendicular to each other? Yeah. And in what direction is this torque? R cross T2 is in what direction?
Clockwise.
It's clockwise, and in terms of a direction, a vector, it's which way? Into the board, right? So RT2 into the board. And that's consistent with increasing theta, the way we chose it, clockwise. It makes it turn clockwise. It makes it accelerate clockwise. And how about T1? Well, the tau has the magnitude RT1, but it's out of the board, so it's got a torque in the opposite direction. It's coming out of the board, right? It's going this way. So those two torques are opposed to each other. There may be one greater than the other one, but the net torque is going to be the difference. And so we get then R times T2 minus T1. Is everybody okay on that? All right, now we've got 6 things that we need to know. We're not quite done. We need 3 more equations here. There was another equation, which is the balance on that pulley. Is the pulley accelerating up or down? No. So there's a net 0 acting on the pulley, up or down. So we have T minus T1 minus T2 minus mg. So the tension in the rope that hangs the pulley from the ceiling is going to be equal to T1 plus T2 plus mg. So that's the equilibrium of the pulley. And we have a couple of more things. We have 2 other conditions.
The accelerations would be equal.
Yeah. Are the accelerations equal?
The magnitude of the accelerations would be equal.
Yeah, their magnitudes are equal in magnitude. But the way we've chosen it here, they can't both be positive. They can't both be accelerating up. They have to have an opposite relation like that. So this is because of stretchless rope. And this is because of the pulley does not accelerate vertically, right? Vertically. And one more condition. It has to do with the pulley.
We have angular acceleration and acceleration.
Right. Angular acceleration of the pulley is related to the acceleration of the masses by the no-slip condition. And if we relate it to A1 and alpha, they're in the same direction, right? Mass 1 moving up is the same as the pulley turning clockwise. So, see a lot of signs in here. SIGINS, S-I-G-N-S, right? That we have, that you got to get right. Plenty of them there, and if you mess up one of them, you're going to get some goofy answer. So you need to be on the watch for signs, and you need to be checking them all along the way. Okay, so we have 6 equations with 6 unknowns, but they're all linear equations, and so we can do some simple elimination here. I'm going to let you work on that in your homework. And it's quite possible I've messed up the signs here or something. Now, I don't want you copying this for your work. I want you to do it on your own, right? I mean, I've gotten you most of the way through it on to help you out here, but I want you to do it on your own. Any questions about this? Is there only one problem for the, God bless, for the homework?
The homework is
Do problems A, 35 and 44 in the book. So
That was A, 35 and 44. Okay, so let me ask a question here. Oh, it's in, let me ask a question before I go take a look at those. What kind of motion is present here? Uniform linear acceleration in the blocks, uniform angular acceleration in the pulley. The weight of the whole assembly is not going to be equal to the 3 weights, the M1G plus M2G plus mg, where m is the mass of the pulley. It's not going to be equal to those 3. Right? Remember, we had this occurred with the Atwood machine. We did this before without the moment of inertia of the pulley. We had that rather surprising result that if this thing is accelerating, it doesn't, the force on the ceiling is not equal to the weights. Very interesting aspect. Number 34 and 35, is that correct?
Oh, that's correct.
35 and 34 and 35?
44.
Oh, 35 and 44. Okay. 35 is very simple, I think. Again, I'll let you work on that one. It's pretty simple. And oh, the yo-yo. Ah, the yo-yo is a good one. Yo-yos.
This just sounds it doesn't sound like it'd be a fun problem.
Now, you need to assume something about the yo-yo, which isn't quite right. A yo-yo won't hang exactly like that, right? A yo-yo really would hang a little bit off. I'm exaggerating here. It's not quite like that either, right? So, but assume that it's on the left, the one that's on the left there. Assume that your yo-yo hangs like that so that the rope is vertical, the string is vertical. Not exactly right, but we'll live with that, okay? So analyze it with that assumption, that the string is vertical. And you are to find the linear acceleration. Okay.
Are we assuming the yo-yo string comes right off the surface too?
Yeah, that's right. Assume that, yeah, it comes right off the surface. So think of it rather than like a yo-yo. Yeah, think of it as a cylinder, and then it's wrapped around the cylinder. Okay, so think of it as a cylinder and a string to simplify the geometry. Whoa. Yeah, that's right. That the string wraps around the outside of the yo-yo like this. So there's not 2 radii that describe, an inner radius and an outer radius. Real yo-yo has 2 different radii. So make it a little simpler here. It's just a cylinder. Simplify it a little bit. Okay. Okay, so the plan of action here is this is the last homework assignment for Chapter 7, I think, and I'll send out the new timing for the assignments. There's going to be one homework for Chapter 8 due on Wednesday. Then the plan is to have a two-part test for Chapters 1 through 7. First part will be on Friday in class. Second part will be on Monday following in class. Okay. So that's because we missed the. I didn't get it done in time. Didn't get you all in time because of our interlude to practice problems. I didn't feel we were ready for the common exam time, which is Thursday, I think it is. So I'm just going to bump it, right? So we're going to use a little bit of class time instead of the common exam time. I'm going to give you a little more time. It's going to be a little bit longer test. It's going to be a lot, and it's going to be in two parts, Part 1 and Part 2. So you'll do Part 1 on Friday, Part 2 on Monday, and it will cover everything from Chapters 1 through 7.
So you said that kind of like replaces the common exam period?
Yeah, we're not going to have any. We're not taking the exam Thursday night.
Okay.
You can do whatever you like on Thursday. No, you can't. You don't need to take a test on Thursday night.
Do whatever you like.
Yeah, I'm afraid somebody's going to hold me to that one. So we'll the fifth homework assignment for Chapter 7 is due Monday, and I'll send you an updated schedule. The schedule for Chapter 8. You haven't seen it yet, probably. We'll do one homework assignment for Chapter 8, then we'll have the tests on Friday and Monday. One long test, 2 parts. Give you a lot of time to work on it.
Yeah. Not 100%. What's the general consensus on what officers?
Me.
Okay, yes, ma'am.
I was just gonna say, since I didn't turn this in at the beginning of class,
Yeah.
I took notes on it in
Oh,
pen,
okay.
so that's what I did in class.
Gotcha.
Okay.
Appreciate that.
No, the homework we gave